Okay? Okay. All right. Okay, so today we'll start with Bayes nets and training Bayes nets and see if anybody gets the idea that we're starting. Okay, let's begin. Today we're going to cash in on all the work we've put in so far on figuring out the notation of Bayes nets and figure out how to learn them. So by now this should be part of what you wake up thinking in the morning. I won't even review it again, but that's the simple one-slide definition of Bayes nets, which you probably know by heart. Yesterday we talked, not yesterday, last lecture, we talked about Markov blanket, and a couple people came up after class and asked a few questions about that. And so I just want to very briefly say again what we said in kind of quickly at the end of last lecture. The Markov blanket, with respect to a variable in a Bayes net, is simply the set of all the variables whose values you need to know in order to completely determine everything you can about this variable. In other words, the rest of the Bayes net is conditionally independent of that variable given its Markov blanket. Okay? And in general, and you'll recall from when we talked about the definition of D-separation, we talked about these three primitive kinds of subgraphs. In general, the Markov blanket for any variable in any directed acyclic graph Bayes net is simply, as it says here, the set of parents, the set of immediate children, the set of immediate parents, the set of immediate children, and then the co-parents of those children. That is, the immediate parents of the immediate children. And why do we need those immediate parents of the immediate children? In order to make the rest of the Bayes net conditionally independent of x sub I given those? Well, we need them because of that funny collider subgraph that was involved in the D-separation definition. Okay? So there's the Markov blanket. All right, so today, and by the way, here's just a list which you can peruse on your own of things that you no doubt know by now since we've covered these. I'm not going to spend the time in class to go through this, but there's also this kind of interesting nice little applet you can grab on the web, and it lets you easily make some nodes and some edges between them and define your own Bayes net and then ask the applet to do some inference on it. So it's a nice way to play around with these ideas and test your understanding. So I thought I would just put a pointer to that up for you. Okay, but today the main subject is learning Bayes nets. And I think the easiest way to think about learning Bayes nets is that there are four problems, or a 2x2 array of learning problems for Bayes nets. And it stems from the fact that we might, or might not, know the graph structure of the Bayes net in advance. Okay, so either we do or we don't. If we don't, we better learn it. If we do, that part of the learning problem is already solved. But of course, we still have to learn those conditional probability tables or some description of the conditional probability distributions associated with each node in terms of its immediate parents. We'll have to learn those, even if we know the graph structure. The other dimension along which learning problems vary in an interesting way is whether we, in the training data, get to observe the values of all the variables in the network. Now, so far in this course, we've always assumed, yes, we do. When we trained our naive Bayes classifier, for example, we assumed there was some variable y we wanted to predict, our class variable, and then all these x sub i's. And of course, we assumed that in the training data, every training example gave us an observed value for each one of those xi's, as well as the corresponding y. But today we're going to consider the possibility that we might have data sometimes where we don't really, on every single training example, get to see every single one of those variables, which is a very realistic problem. For example, if you imagine training a graphical model, a Bayes net, to classify patients, medical patients, according to predict their disease based on their symptoms. Usually when I go to the doctor, they don't put me through every possible test. They just look at 4 or 5 things. And then there are a lot of unobserved variables like, you know, what's Tom's white blood cell count? Well, we don't know. We haven't measured that yet. Maybe if he was really sick and there was a good reason, we'd pay the extra money to measure his white blood cell count. But it might be unobserved. So there are plenty of practical situations where we might have data where some, but not all, variables are observed. Okay, so then it turns out in that 2x2 grid of problems, known and unknown graph structure, fully observed, only partly observed variable values. As you might expect, the easiest problem is where, yes, we know all the variable values. It's fully observed data. And yes, we know the graph structure in advance. And so that's the easiest one of the 4 problems. The problem we're going to consider today, in addition to that one, is the problem where we know the graph structure, but we don't get to observe all the values of all the variables all the time. And that's as I mentioned, that's a pretty interesting problem. Now, people do also work on what I would call the gruesome case of not being able to fully observe the variables and not knowing in advance the graph structure. But as you might guess, that's a more difficult problem, both in terms of working through the mathematics of what you want to do, but also in terms of the sample complexity, you know, the amount of training data that we would need to have in order to learn, estimate both the graph structure and deal with the fact that we don't observe all the data. So we're going to look at the easy case and the interesting case today. All right, so let's start with the easy case. Here's a now familiar Bayes net. With a midterm coming up, it's good to think about what are the general lessons of the course so far. And so one of the general lessons, to put it in kind of a Jeopardy mode, is the answer to the following question. Is that right? Oh, yeah, MLE is my Jeopardy clue. And your Jeopardy answer is, what is our standard way of deriving a training rule when we want to learn some function or when we want to estimate the parameters of some probability distribution? And of course, maximum likelihood estimates has been our tool of choice, and so have MAP estimates, maximum a posteriori probability estimates. So, and of course all that means, all MLE means, is that we want to choose, well, again, we'll use theta as the symbol for representing the different parameters that we want to estimate for all of the conditional probability distributions and for all of the variables in our network. And in general, we've said, well, if we've got a learning problem where we need to use our training data to estimate the values of the parameters in the function we're trying to learn or the probability distribution we're trying to learn, then what we'll do is we'll try to find the values of those parameters, the value of the vector of theta parameters, that maximizes the probability of the training data. So if you give me 2 different choices for what the theta values could be, I'm going to take the one that makes the observed training data more probable than the other one does. Very intuitive thing. And it turns out that that's a very reasonable way to derive a training rule for Bayes nets too, right? I mean, that's basically what we did for naive Bayes. and for logistic regression when we actually got the maximum conditional likelihood estimate. And if we do, we get a training rule that looks a lot like what you've already used for naive Bayes, for example, which in a way shouldn't surprise you because, as we know, the naive Bayes classifier is just one special case of a Bayes net anyway, as we discussed a couple lectures ago. So, for example, if I use the symbol theta sub s given ij to indicate one of the parameters in this Bayes net, there will be, for example, of course, there will be a conditional probability table associated with every node in my network. This one will give me a table where I have to estimate the probability that S equals 1 or 0, given that flu and allergy are known. And of course, they can be known as either both zeros, or a 0 and a 1, or a 1 and a 0, or a 1 and a 1. Right? And so in this table, basically I'll be interested in those 8 numbers, those 8 probabilities, indicating how the probability of S being 1 depends on the known values of flu and allergy. And so if I use this symbol to represent the probability that S is 1 given that flu equals I and allergy equals J, then the maximum likelihood estimate for that parameter is exactly the same kind of maximum likelihood estimates we used when we tried to guess the probability of a coin coming up heads, or when we tried to guess the probability that X sub I in our naive Bayes classifier would be 1, conditioned on its parent in the Bayes net, conditioned on Y, right? And so today I'm going to use this symbol delta to mean this will be 1 if its argument is true. Else 0. So basically my maximum likelihood estimate for this is just the ratio of how many of my training examples, so K here is the kth training example. So basically this is just counting the ratio of training examples for which, in the denominator, for which F and A take on the values I and J. And the numerator is the examples where that's true, and of course also S takes on the value 1. So it's just the proportion of relevant examples for which S equals 1. Our standard maximum likelihood estimate. Yes? Sorry, in this example, do you know? You know the graph structure, right. So here I'm assuming we know that network, and we're simply trying to estimate the parameters of all the conditional probabilities for all the variables in that known graph structure. Okay, so I'm telling you this is what the answer is, but you should ask yourself, well, how would I prove that to myself? What is it that you would want to prove? Well, what you want to prove is that the maximum likelihood estimate for training a Bayes net, which means really estimating not just this one theta, but all of the thetas for all of the nodes in the network. What you want to do is you want to prove to yourself that the likelihood of the data, the probability of the data given the entire set of parameters, is maximized if we use these kind of maximum likelihood estimates individually on every parameter in the network. Okay. And it turns out that's pretty easy to do. Let's do it. Here it is. So if we wanted to prove this, the way we would do it is we'd say, well, of course, maximum likelihood means that we want the theta that maximizes the probability of the observed training data given theta. And so we have to start by writing down the expression for the probability of all of the training examples given theta. How do we do that? Well, that's here. The probability of the data given theta is just the product over, again, this is our kth training example. The product over every training example, we'll assume they're IID, independent, identically distributed training examples, independent training examples. Then if you give me 100 training examples, the probability of that set of 100 training examples is just the product of the probability of each one, since they're all independent. And the probability of each one is just the probability of their observed F, S, A, H, N values. And of course, we know that in this particular Bayes net, with that particular graph structure, we can write it by factoring that joint distribution, as we have for the last several lectures, into these different terms that fall right out of that graph structure. And then if we want to maximize the probability of the data given theta, we can just as well maximize the log of that, which means the sum of the logs of those different training examples. And now the nice thing comes in. This is the nice thing that's going to turn out to allow us to train every parameter separately, ignoring the others, essentially, by just getting little local maximum likelihood estimates of each one. And that's because the log of the data given theta, that factored thing turns into the sum of their logs. And so now when we want to maximize this, we use our standard method of let's take the derivative and set it to 0. Well, when we take the derivative with respect to, let's say, this one parameter we just talked about, theta, where the particular theta out of this entire vector, the particular theta where s equals 1 and the parents take on the value I and j, well, the derivative of this first term with respect to that parameter is 0. The probability of f is not influenced by that. It has its own parameter. And so the only term out of this expression that actually is influenced by this is, of course, the one where the term where we have s depending on f and a. And so now the nice thing that happened here is that when we try to optimize that thing by taking its derivative, in that sum of log likelihoods, most of those derivatives end up being 0. And so now we just recall, well, if you work through the arithmetic, it's identical to what we did before now. This you might even recognize from before. Just turns into saying, well, if you take this derivative, work it out, set it to 0, then the solution is theta equals that, which is what we just saw. Okay, but I wanted to go through that partly as review, because this is just another instance of the same template of approach that we did before when we derived the training rule for logistic regression, when we derived the training rule for naive Bayes, when we derived the training rule for the single parameter associated with flipping a coin. In all these cases, what we do is we say, well, what we want is to derive a training rule that will have the property that it will give us the theta that maximizes the likelihood of the training data. And so this is the standard approach. And if we apply it again here, you can see what this is telling us is, okay, to train the entire Bayes net, you can basically independently estimate each of the parameters with a simple maximum likelihood rule, formula that's exactly the same as a coin flip formula. In the case where the graph structure is known and all the data is fully observed. So it's very simple. It just reduces to a problem we've already covered. Okay. Now, the more interesting problem. What if this data is only partly observed? What does that mean? That means for some training examples, I will not see all 5 of the values of all 5 of the variables in my BaseNet. Instead, maybe on one training example, I won't see headache. That won't be observed. But I'll see the other 4. On another training example, maybe I'll see all 5. On another one, maybe I'll see everything but not sinus. Okay, that's what I mean. Then what do we want to do? So we just went through what we would do if it was fully observed. We would get our maximum likelihood estimate. But here, let's consider what's really happening. We can't really calculate this anymore because we don't really know what some of those, if K is the index for the different training examples, for some of the training examples, we don't actually have all 5 of these values. In fact, just to simplify our notation and our thinking, let's consider a slightly special case, but everything we're going to say generalizes back to the full case. Let's consider the special case where the things that are observed are always observed, and the variables that are not are always not. Let's assume that. So for example, let's just look at the special case where, let's say, sinus I never get to observe, but the other variables I always get to observe. So that's a little less general than different things being missing on different examples. The ideas and the approach we're going to derive generalizes to the full case, but it's easier to speak about and think about that slightly specialer case. So let's do that. So then I'm going to, let's say, given all 5 of these variables, F, A, S, H, N, I'm going to use X to refer to the ones that are observed. And in our case, let's assume that's F, A, H, and N. That'll be our observed variables. And let's say Z we're going to use to refer to the variables that are not observed. Let's suppose, for the sake of argument, that's S. And so now, when I say I want to maximize the likelihood of the data, that's the same as saying I want to maximize the probability of all my variables given theta. And now I'm just pulling that out into the observed and the unobserved ones. So my question is really, given that we can't optimize the objective we had before, the likelihood of the data, because we can't calculate it, we can't observe we can't observe the S variable. What should we set as our new aspiration, our new objective to try to optimize while we train this network? Thoughts? Well, you know, one thing we could do, of course, is just ignore the unobserved variables. Although that's kind of hard because our definition of the joint distribution mentions those unobserved variables. We can't quite do that. Marginalize them out. That's a good thought. Right. And so what we're going to do is actually pretty much that. In fact, the algorithm that we're going to consider, instead we're going to take the argmax again over theta. Well, we'd like to maximize this. Notice I'm leaving a little space here. We'd like to maximize this. But since we can't observe those z's, what we're going to do is just take the expected value of this with respect to p of z, given the observed stuff. Okay, so what we'll do is we'll take the expected value of this thing with respect. Now, whenever somebody says take the expected value, the first question you should ask them is, with respect to what probability distribution? Right? The expected value of something is just the average of its possible values weighted by their relative probabilities. And so we're going to take the average of this likelihood with z, the unobserved stuff, weighted by the probability that the unobserved z in this particular training example would be 1 versus 0. But what probability distribution are we going to use to get that probability distribution on the unobserved data? Well, the obvious thing to do is we'll take the probability of z given x and theta. Okay, so this is like marginalizing out the unlabeled variables. What we're saying is, okay, we'll still consider the full set of variables because that's what the Bayes net lets us easily calculate the joint distribution on. But now we're going to just take the expected value of that to deal with the fact that the z's are not observable by us. What we're going to do is take the expected value of that using the probability distribution over z given the observed variables. And of course, as we talked about last time, once we have a Bayes net, we can calculate any of these conditional probabilities that we like. In this case, this is the probability of the variable s given FAHN. And you know how to do that. You know several ways of doing that, some more tractable than others. Okay, so this might be the most important thing in today's lecture. Just as important as maximum likelihood, the notion of maximum likelihood being the basis for deriving training rule for naive Bayes, for logistic regression, for lots of things that we're going to be talking about, or map. And now what we're saying is, well, if we can't observe all the variables, then instead of maximum likelihood, let's just take the expected, the theta that maximizes the expected log likelihood of all the variables. And that expectation is taken over probability distribution that we can calculate from the Bayes net if we knew the theta values. And so that's the thing we're going to try to optimize. Yes?
Yeah, what I was really thinking about was like summing the p of x and z given theta in the original, saying sum it with respect to the z. So that thing seems quite different from this.
Well, this is pretty close to that because, see, what you're going to do is you're going to take this is the joint likelihood of all the variables, but when we substitute z equals 1 here and z equals 0 here, we're going to consider both of those possibilities, but we're going to take the expected value, which is we're going to weight the case where we plug in a 1 for z by the probability that z is actually 1 given the other observed variables. Yeah, plus we're going to weight the value when z equals 0 by the probability of that.
Well, it's like you're putting the weight on the log values, not on the correlation.
Exactly. So it's not exactly the same as what you're proposing. But this is the method we're going to use. And it turns out there's a nice algorithm for doing this. And so if you come up with a nice algorithm for doing yours, that would be good too. All right, so let's look at this. I think we just did this, right? Okay, so EM is going to, so we have an algorithm, we'll call it EM. EM stands for expectation maximization because we're maximizing the expected value of this joint likelihood, the full likelihood, taken over the distribution on the unlabeled data conditioned on the the unobserved variables conditioned on the observed variables. And EM stands for expectation maximization because it's picking the theta that maximizes this expected value of the likelihood. And now it turns out EM is this nice algorithm for doing that that is guaranteed to at least find a local maximum, a value of theta that locally maximizes this expected log likelihood. All right, so let's look at how that works in some detail now. Let's work through an example. So here, as we said, EM, we want to maximize that expected likelihood, again, written at the top. And here we have our particular 4 variables observed, 1 not. Here's our same formula for the full likelihood, the likelihood of the set of observed and unobserved variables given theta for that particular network breaks down into this sum of logs, just like we saw before. And now when we want to take the expected value of that, what does that mean? Well, it's just like taking the expected value of anything. It just means we take that quantity that we had up here. But now, since we don't know the value for our unobserved S variable, what we have to do is we have to take a weighted average of that quantity for the case where S equals 1 and S equals 0, weighted by the probability that that's happening. Okay. So that's simply the formula. That's all it means, really, to take the expected value of that likelihood. It just means we're averaging together with these weights the likelihood under the 2 possible values for the unobserved S. And now you might ask me, well, Tom, let's be real. If we don't know theta, we don't know this distribution. So how can we calculate the expected value? I agree with you. We got a problem, and that's the beauty of EM. EM is an algorithm that manages to maximize this despite the fact that we don't yet know the theta. So let's see it. Here's the EM algorithm. So it's a general procedure for learning, in this case, of partly observed data. And the way it works is we take this quantity that we agreed we want to maximize, and we do a little trick. The little trick is this. We treat the theta that we use up here and the theta that we use here as temporarily 2 different things, because we don't know theta. So what we do is we define this function that says, well, basically what we're going to do is this. We're going to start with a guess of what theta might be. We're going to use that guess, let's call it theta, to calculate, we'll use that theta guess to calculate P of z given x and our guess for theta. And that will allow us to calculate those expected values for each one of our training examples, just like we saw in the previous slide. Given that those probabilities for the unobserved S variable from our guessed theta, we now plug those in and we get our formula for the expected full data likelihood. And now we change our theta, we pick a new value which we'll call theta prime, which maximizes that full formula. We'll go through an example of that because it's a little bit of a brain twister when you say it that way. But it turns out to result in the following incredibly simple 2-line algorithm. We start with our guess of theta. In the E step, the expectation step, we calculate those expected values for every one of the training examples for every one of the unlabeled variables. Okay, so that's what we're doing. In the E step, to calculate this, and in particular, the value of each unobserved, well, I'll just say variable in Z. Z is our unobserved variables. For each training example. Okay. Now we plug that into our expression for the likelihood. Where's our expression for the likelihood? There it is. So we plug that in for these, and then we pick the theta that maximizes. Essentially, there's an implicit theta on which all these other things are conditioned. So we get the thetas that maximize those. So these are the expectations okay? And then there are implicitly these thetas. I could do it this way in all these. Okay, and then as I mentioned, the nice thing is this does a kind of hill climbing. We just iterate this process. So now we choose the theta prime that maximizes that. We assign our new guess to be that theta prime, and we go ahead and repeat this process. And each time through this loop, of course, we have to go back to every training example during the E step. We have to go through every training example and every unlabeled variable and estimate its expected value conditioned on this theta that is our current guess. Okay, so let's do this. Okay, so if we actually want to do this in our example-based net, so that we take it all the way down to the level where you could program it yourself, although we won't ask you to do this one. Then in that E step, if I give you a set of training data where we don't observe S, but we observe the other four variables, and I give you, let's say, 100 examples, on each one you observe these four variables, then we want to apply EM to train the thetas for all the, for the entire network, including S, including the conditional probability distribution associated with S. Then on the E step, we have to go through every training example and basically calculate the probability, the expected value for S, given the observed values F, A, H, and N on the kth training example. So who can tell me the formula for doing that? Hint, there are exactly 3 terms in this formula. Hint, go back to the definition of conditional distribution. Okay, what's the definition of conditional distribution? This is just the probability of S equals 1 and our other observed values over what? Right, right. Over this. Whoops. Over that. Right? Which we can also write as equivalently, we could write that as, what could I put on the denominator instead? I could put this. Plus the probability that S is 0, given those same things, and those same things. Because obviously, the denominator I wrote the second time is equal to the denominator I wrote the first time. Yes?
Should all those have given thetas, or is theta sort of the equation?
Should all of those be given data?
Given theta.
Oh, theta. Yeah, I agree. So I could put a theta. You get the idea.
Should it be n theta or given theta?
It makes my editing process a little more complicated, but you're right. Conditioned on theta. All these things are essentially conditioned on theta. Theta is the thing that defines our probability distribution. Okay, so now you got it all the way down, right? So EM is really a very simple algorithm. We don't know the values of these variables. So what we do is we set up this iterative procedure. We make up a theta to start with. Then we use our theta to estimate the expected value of every one of those missing variables in every one of those training examples. In our particular example, we just wrote down the equation that we would use for the E step. This is exactly what we would do on the E step, using our current theta. Okay? Then we plug that in to weight the likelihoods of all the examples to write down the expression that we had 2 or 3 slides ago. And now we maximize that expression with respect to theta, but we've already frozen these estimates, these expected values. So when we take the derivative, this use of theta is no longer around. We're just using this to calculate the expectations for S. Okay. So that's just what we said. Today I decided, because my handwriting is not so good, a lot of these slides have the full answer printed out after I write it sloppily to help you. Okay, so here's what it boils down to in our case then. In the E step, we calculate the expected values of all of the, again, K is our index for the kth training example. We just calculate the expected value of S for the kth training example for all Ks. Then on the M step, we derive a new theta which maximizes that likelihood. Oh, well, that turns out to be just like our maximum likelihood estimate that we had before, except now we are taking, for example, to find the probability that S equals 1 conditioned on its parents taking on the values I and J, instead of taking our old MLE, which we would use if we could see all those values, we now have one that looks just like it, except that instead of essentially counting S as a 1 or a 0, we're treating it as it's some expectation. It's going to, in this case, be the expected value of a Boolean variable is going to be somewhere between 1 and 0. In fact, it's going to be exactly the probability that it's 1. That's what it'll be. And so what we're doing is essentially, it falls out if you work through the math and really write down that expression for the condition, for the expected value of the joint, of the full likelihood. And if you take the derivative of it with respect to theta, the same way we did at the beginning of the lecture for the MLE, you'll get a very similar derivation. But instead of coming up with this expression, you'll come up with this one that has that expected value of S in it. So intuitively, what's happening here is those unobserved variables, well, we guess what they are. We guess literally their expected values. And then we use those expected values kind of in place of the observation. And every iteration of EM, you can prove on every iteration, the objective function we're trying to maximize, the expected full likelihood, is a non-decreasing quantity over iterations. So it either goes up or it stops. And if it stops, we're done, because we've hit a local maximum, and that's all we can guarantee, actually, since arbitrary Bayes nets might or might not have a concave, present a concave optimization function to us. Okay, so there's the EM algorithm. Now, we did this for this particular Bayes network, but in fact, the derivation we just went through, if you actually work it through in detail, you'll see it doesn't matter what the Bayes net structure is. If you give me, for example, a Bayes net structure of any kind based on, let's say, some set of observed and unobserved Boolean variables, then the EM procedure will always boil down to, on the E step, calculate the expected value of each one of those unobserved Boolean variables. And on the M step, just essentially replace the count of the number of times the variable was 1 versus 0, replace that count by its expected value, the expected number of times it was 1 and 0. And of course, on any given training example, you might say, well, the expected value on this one is 0.8, and this one is 0.5, and this one is 0.6. You just sum those together, and that gives you the expected total count. So it's that simple, actually, in the case of Bayes nets with Boolean variables. We just essentially use a formula that turns out to be our old MLE formula, but with the counts replaced, in the case of the unobserved variables, by their expected counts. So it's a beautiful, beautiful thing indeed, because the algorithm is simple. We do have to iterate it. But in many practical cases, like this one, it would converge quite quickly. You probably, fewer than 10 iterations would probably get something very close to a final answer. Okay. So there's the EM idea. You see how big this is. This is big. It's big because Bayes nets cover a lot of problems we want to be interested in. Why? Because Bayes nets are a general notation for representing any joint distribution over random variables. The problem we started the semester with, function approximation, is just a special case. That's just estimating P of y given x sub 1 through x sub n. That's a special case of a probability distribution we want to estimate. EM is a general procedure for any Bayes net for training it to estimate the thetas when some variables are observed and some are not. So that's why it's big. It's very general purpose. It covers a lot of the kinds of problems that machine learning wants to do. And it's very pervasive in the field. People use this all the time. Okay, so now it actually gets to be fun. Let's go back to a problem that we know well, naive Bayes. Now, you did a homework on this. You implemented naive Bayes. You're experts. When you did your homework, of course, you assumed the training data that you had involved fully observed data, of course. And we didn't bother to give you any data of the form, well, here are the example features, but I'm not going to tell you the label. We didn't bother to give you that. And if we had, you would have said, okay, but now you won't do that, right? Now if we give this, you'll say, great, I can finally use EM for something interesting. So let's do it. How would you? What if you had that homework to do again, but now we give you this kind of data? So what would you do? You actually can work this through. So what we're going to do now is the same thing as before. We have a Bayes net happens to be the naive Bayes net, right? Because y is one variable, and all the x sub i's are conditionally independent given y. That's all that Bayes net says. And so given this partially labeled data where you don't know all the target values, you don't know all the y's, you're going to use EM. That means you're going to have to put together a procedure where iteratively, so you'll guess some thetas. What are the thetas in the naive Bayes? Oh, those are just the probability that y is 1 or 0, and the conditional probabilities of each x sub I given y. That's all that we did in naive Bayes. They're exactly the conditional probability tables you would get if you just wrote down the tables that fall out of that Bayes net structure. So on the E step, we need a formula for estimating the values of the unlabeled variable y. That's what it was in that table. So on the E step, we're going to estimate the probability that y sub k is 1 given the observed values, x sub I k. And we'll have to estimate 2 of those expected values on each E step. And then on the M step, what do we do? We'll just retrain our naive Bayes classifier. Instead of using the count of what fraction of the y's were 1, we'll now, well, we know what these are, but these we're going to use the expected value of y and the expected value of this y. Right? Okay, so how would we get that expected value? What's the formula for the expected value of y? So we want the expected value of y. And again, what's this expectation taken over? It's the expectation of y, the unobserved variable, given what? All the observed variables, right. X sub 1 through, what did I call it? X sub 4. That's the distribution we're taking this expectation over. Okay, how do we get that? Oh, that's easy, right? That's just can we read that right off the conditional probability entries in this Bayes net? Is that one of the thetas that's already in the Bayes net? What are the thetas that are in this Bayes net? What are the parameters associated with y? Yeah, p of y equals 1. And by the fact that it must sum to 1, also implicitly p of y equals 0. What's this conditional probability table associated with an x sub I? Right, it's just its probability given its immediate parent. Oh, well, that's, of course, just what we always estimated. That's exactly what, these are exactly the 2 quantities we were always estimating when we trained naive Bayes. And that's why. It's because those are the conditional probabilities in the naive Bayes net. Okay, so these are the things we have available when we guess our theta. We're guessing values for these kind of things. Now we need this. So how can we calculate that from the parameters available in this Bayes net? Use Bayes' rule, absolutely. So that's easy. So that's just by Bayes' rule. Right? And actually, to make this a little clearer, I could have written explicitly a value for y here. Again, you know, anytime we kind of leave out the actual variable equals value thing, we're kind of just abbreviating notation. So I just unabbreviated it there for y so that we could be clear on what we're doing. So the probability that y takes on the value k, conditioned on x1 through x4, by Bayes' rule is just this thing. And that denominator is just equal to the probability of x1 through x4, right? Because essentially we're marginalizing out the y variable. Okay, so Bayes' rule tells us how to get these. So that is the expected value of y. That is our E step. So on the E step, we're going to take our thetas. I guess I could have said given theta. I'll put a little theta in here again, like that. That's a vector of thetas. So on the E step, we get the expected value of y using the distribution of y given the observed variables and our current guess of theta. By Bayes' rule, that's just this. And this is easy. Oops, I haven't quite turned it into something we can use from our Bayes net, because I still have this p of x1 and x2 and x3 and x4 given y. How do we deal with that? The conditional independence assumption, of course, says that this equals the product from 1 to 4 of pxi given y. Right? That's the conditional independence assumption that we can vary. Okay, so now we've reduced it to a bunch of terms that correspond to the theta estimates that we already have. So basically, now we have a formula where I could plug in for each of those p's. I could plug in some theta, that some particular single scalar theta component of the theta vector, and use that to estimate the expectation of y for that particular kth unlabeled example. In other words, if you look at that formula, it's the same thing we use when we classify a new example given a trained naive Bayes classifier. So all we're doing is we're using our current theta. We're treating it as a naive Bayes classifier, and now we're classifying the unlabeled data. Probabilistically, we're saying, well, given these x's, how would you predict the value of y for this? Well, 0.7, it's 1, 0.3, it's 0. The formula we just wrote down is exactly that. This is just another way of getting at exactly what we did when we derived the inference rule for naive Bayes. But now you see it's exactly what we would use in the E step. And then on the M step, what do we do? Well, on the M step, we just replace the estimates get to be just like MLE, but again, we use the expected counts. So instead of taking, if all of our y's were observed, we'd estimate the probability that y is 1 by the fraction of those observed y's that were 1. Now, instead, we have to use expected counts for the cases where we didn't get to observe them. So in the E step, we essentially label, we apply our naive Bayes classifier to label all the unlabeled examples probabilistically. On the M step, we retrain the same naive Bayes classifier now to get a different set of thetas because we just changed the labels that we assigned to the unlabeled examples. So you get the intuition of what's happening? If I hadn't even mentioned EM or done any of this, any of these formulas, if I'd started this lecture by saying, if I wanted you to train your naive Bayes classifier, and I gave you some unlabeled examples, what would you do? You might have said to me, well, I don't know, but here's a heuristic idea. We could train it just from the labeled examples, and then we could use that trained classifier to assign labels to the unlabeled ones. And then we could go back and retrain it using not just the observed labels, but also those predicted ones, those assigned ones. And then I would have said, oh yeah, but the assignments you're making are not ones and zeros, they're probabilities that things are ones and zeros. And you would have said, yeah, okay, let's use the expected values instead. And you would have come up with this EM algorithm that way. I mean, basically, it is a very intuitive thing. It says, okay, use your train classifier, assign labels to the unlabeled y's, retrain. Keep doing that until things no longer change. That's how we would apply EM to naive Bayes. Now, fortunately, we're not even the first people to think of this. Kamal Nigam, shown here in an early photograph, one of my former PhD students, for his PhD thesis, explored the question of how could you train systems with combinations of labeled and unlabeled data. And one of the things he did was exactly apply EM to naive Bayes. And let's look at what he came up with. So here's the algorithm that he published. If you read this now, you see that, what are we, like 6 weeks into the semester? I don't know. This many weeks into the semester, you're already at a point where you can now read research papers and make sense out of them. Here's his algorithm. He applied this to document classification. And look at his EM step. So basically he says, here's the EM algorithm part of it. While the classifier parameters improve, as measured by a change in the log likelihood, this is actually the expected, this is the quantity that we're trying to maximize, the expected log likelihood. Use the current classifier, he's calling that theta hat, the current estimate of the parameters, to estimate component membership of each unlabeled document. That is, the probability that each class, each y value, generated the document. And then on the M step, re-estimate the classifier, given those estimated components. Okay, so he applied this to several document collections that you know. And what did he find? So one of the document collections was the WebKB data set. It's a collection of web pages labeled by things like, is this a course homepage or a student homepage or a research project homepage, etc. And what this slide shows is the result of two iterations of EM applied to that, where he trained, what does it say there in the caption? He doesn't tell us in this caption how many labeled examples he used, but I'm sure it was under 5. It was a very small number of labeled examples. I think it was 1 or 2 per category. And now what he's showing here is the rank order of all the thousands of words in the document, ranked by their the probability that the word will occur given that Y is a course page divided by its probability given it's not. So it's the ratio of the likelihood of W. Okay, so basically this is telling us things high on the list are things that the classifier believes are good indicators to separate Y equals course versus Y equals not course. And so on iteration 0, oh, now I remember. It was, yeah, I think it was one training example, which happened to be a course page from Dartmouth on artificial intelligence. You can kind of guess from looking at this. And the DD is just a token for meaning it's a pair of digits. It's just a way of abstracting away from 13 and 23 to make them the same DD token. Okay, so that's what he had initially, just training on the one labeled example. Then after one iteration of EM, so what happened in that iteration? He took that really simple classifier that was trained from one training example, and he applied it to many other, hundreds of other documents that were unlabeled, got the expected values of their Ys, and then retrained. When he retrained, he got a different ranking of the different features. You did that again, and on the next iteration of EM, here's the ranking of features. Now, what's interesting about this is you can see just kind of with your just looking at these lists that the list on the right is much better than the list on the left in terms of general coverage of course pages. You know, it has things like those things with the D's in them are probably course number kind of tokens. Lecture, due, homework, assignment. That's pretty good. So at some kind of intuitive level, you can see what happened. He also looked more quantitatively. He also used the news groups data. And this is a plot that shows if you use only 20 labeled documents for the 20 news groups, that means you have one labeled example of each news group. And 10,000 unlabeled examples. Then if you just use standard naive Bayes, just training on the one labeled example, the test set accuracy is at that level. But if you use EM instead, you get substantially higher. So this is essentially the EM curve, and this is standard naive Bayes. So kind of interesting. What it's saying is, especially when you don't have much labeled data, using that unlabeled data with the EM algorithm can boost your actual test set accuracy classifying new documents quite substantially. The other thing you see is if you increase the number of available labeled examples, then the marginal value of adding in EM to take advantage of the additional unlabeled data isn't as great. You already know, you're already approaching your asymptotic, you're closer to your asymptotic in the number of labeled examples accuracy, and so you kind of don't expect the unlabeled data to help as much. But there you can see it. EM, and it has a very positive impact in this kind of very practical problem. Here's another graph from the same data set. This one shows us not how the performance varies if we increase the number of labeled examples, keeping the unlabeled examples constant. This one shows if we keep the labeled examples constant and we increase the amount of unlabeled data, what happens. And so here you can see basically the more unlabeled data, the better. That should kind of jive with what we would guess. We never figured out why there's this weird little tick at the beginning. We were hoping it's some kind of variance in the that you get because you have so few training examples. And you also see that for each of these curves corresponds to a different number of labeled examples. So for example, this one is the 3,000 labeled, and this one is 40 labeled. And so again, you see the less labeled data you have, the greater the boost you get from unlabeled data. And the more important it is to use a lot of it. Whereas if you started with 3,000 labeled examples already, even adding thousands, 10,000 unlabeled documents doesn't really help that much. You're sort of getting close to saturation in your estimates of those thetas just from the label data. Yes?
On the previous graph, so you said naive Bayes is basically having EM with 0 iterations, right? So how many iterations was that graph from?
These were on the order of less than 20 iterations. So EM often converges fairly quickly. Yes?
So these are for Boolean values in class class.
Let's see. Y is Boolean here. The X's were exactly the formulation you used. So it was the multinomial model where every position in the document is a random variable that can take on one of 50,000 word values. And then also this assumption that all those word positions have the same distribution.
So if y had 3 values or 4 values, then with this graph, would like the 3 values would 80 labels be?
Ah, I see. So it's a good question. The question is, how would this graph vary if y was not Boolean but could take on, say, 10 values instead of 2? I don't know. Oh, here it takes on 20. That's right. That's right. So, duh. Yeah, here it takes on 20. But I don't have an answer. Maybe somebody does to how would we predict this graph would change if we varied the number of values y could take on. By the way, these kind of questions are great midterm practice questions. Questions of the form, how do we predict this graph would vary if we changed this property of the training data? They are very good questions to think about as the midterm approaches. Because again, they're the kind of questions that if you understand it, you can answer those things in 60 seconds. If you don't understand it, you should. So when you get in your study group, you should ask each other those kind of questions. And feel free to ask ones whose answers you don't know, because you might learn something. All right. So I want to get to a wrapping up point, and we're just about there. So what have we seen? Here's, it's actually a very simple but very important story from today. We can train function approximators, Bayes nets more generally, with combinations of labeled and unlabeled data. And what it takes to do that is to come up with a different principle for what's the objective we want to optimize. We can't say we want to maximize the observed, the probability of the observed training data because we're not observing all of the variables in all the examples. So what we did instead, we said, okay, we'll generalize that actually by saying, let's maximize the expected likelihood of the data, probability of the data given theta. Let's maximize the expected likelihood of the data, where that expectation is taken over the probability distribution on the unlabeled variables given the labeled variables. And then the EM algorithm does exactly that. In fact, it's guaranteed to reach a locally optimum value of theta that locally maximizes that objective. And it does it with this fortunately simple procedure of iteratively guessing a new value of theta, the vector of all the thetas that we need, using that current estimate of theta to guess the expected values for each one of those unlabeled variables in each one of the training examples, and then using that to get our new estimate of theta that that relative to the old theta now maximizes the data likelihood, the expected data likelihood. Then we saw that we can relate this back to naive Bayes, something we know well. It actually is very practical. And now the question I want you to think about for next time is this one. No doubt you've heard about clustering. It's a very obvious idea. The idea of clustering is, well, what if I have data that has no labels? What's a good way of clustering that data into groups? And I just want to point out before we leave, so you can think about this before Tuesday, that question is just a special case of the question we just discussed. The question we just discussed is this one. I want to get back to, there it is. We just discussed this question. How would we train a naive Bayes classifier to decide whether this example fits into group 1 or group 0 of the possible x's? How would we, and we asked, well, how would we do that if we don't have, for every example, a label of which group it fits into? What if we only have labels for some of those x's? about which group they fit into. And so the question of clustering is no more than the question of saying, well, what if these are all questions? What if we have no labels? Okay? And so that's what the clustering question is. So in a sense, you already know the answer to what would be an interesting, probabilistically grounded way of clustering data. You could say, well, I already know how to train with some missing values. Let's just make y the missing value and, for example, retrain my naive Bayes classifier with no labels and just run EM. Would that make any sense? Well, you'd be maximizing the expected log likelihood of the data with the expectation over the probability of these unknown y's given x. So that's, in fact, an approach that people use. They call it a fancy name, a mixture of Gaussian clustering or mixture of multinomial clustering. It's exactly this. It's exactly the idea of taking naive Bayes and removing all the labels. Or even non-naive Bayes and removing all the labels. But, so next time we'll talk about clustering and take it from there. Thanks. Homework 2.